Hello, welcome to the 22nd class of this course. In this class, I will talk about orthogonality of Bessel functions, normalization of Bessel functions, and Bessel series. But before that, let me summarize what we did in the past few classes. So we introduced the Bessel differential equation, which is given by this, and we derived the solution of this Bessel differential equation, that is the Bessel function of first kind. And then we derived, we talked about, we mentioned another linearly independent solution of this Bessel differential equation, and that is the Newman function or the Bessel function of second kind. And then we talked about the generating function, which is another way of deriving the Bessel functions rather than solving this differential equation. And then in the last class, I talked about some recurrence relations related to these Bessel functions. And in this class, I will talk about the orthogonality. But before talking about the orthogonality specific about these Bessel functions, let me talk about the orthogonality in general. What do we mean by orthogonality in case of functions? Because in our 10+2 physics, we know about these orthogonal vectors, right? So those vectors are those vectors will have a 90-degree angle between them. So those we will be calling the orthogonal vectors. And another property will be the dot product between those two vectors will be 0. So similarly, what do we mean by orthogonality when we are talking about these functions? So let me explain that. I have already explained the orthogonality of functions in great detail while talking about the Legendre polynomials. So I will give the link in the description section where I talked about this orthogonality of Legendre polynomials. So if you want to know orthogonality of these functions more, then you can just go through that video. So let's talk about what do we mean by inner product, because in case of vectors, we know that we will call two vectors orthogonal if the inner product between them is 0. So in case of functions, what do we mean by inner product? That's stated here, that the inner product between two functions fx and gx on some interval a to b is given by integration from a to b f star x times gx dx. Okay, so it's the integration of these two these two functions, multiplication of these two functions. And as the inner product is defined like this, then the orthogonality between two functions is stated as this inner product is 0. So when this inner product becomes 0, then we will call this fx and gx, these are orthogonal. And similarly, when this inner product of a function with itself becomes 1, that in that case we will call the function set as normalized. So it's similar like a Cartesian vector having a length 1. In that case the inner product with itself will be 1. Those are the unit vectors basically. And we also know that, for example, in case of Cartesian vectors, let's say we are getting in case of 3 dimension, we are getting 3 orthogonal vectors, for example I hat, j hat and k hat. And in that case, any vector in the 3 dimension we can write as some linear combination of I hat, j hat, k hat, and that means like c1 I hat plus c2 j hat plus c3 k hat. So any vector in 3 dimension I can write like this. Similarly, if we get a set of orthogonal functions like f1, f2, f3 dot 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 on this interval x equals x2 x from a to b, then any well-behaved functions, for example hx, can be written as a linear combination of the set of orthogonal functions, just like we did in case of orthogonal vectors. So this is how any function in the interval a to b, it can be written as a linear combination of these orthogonal functions f and x. And also this orthonormality, what do we mean by orthonormality? It's basically orthogonality plus normalized. So for example, if we have functions like f1x, f2x, f3x, then those set of functions we will call them orthonormal if they satisfy this condition. So where this delta of mn, it means that when m equals to n, then this delta of mn will be 1. So it is 1 when m equals to n, and it is 0 if m not equals to n. So that means if we are doing the inner product between two different functions, then the inner product will be 0. That means they are orthogonal. That's the orthogonality. And if you are doing inner product with itself when m equals to n, then that is 1. So that is the normalization. And if any set of functions satisfy this condition, then we will call them orthonormal. We will call the set of functions as orthonormal functions. So that's what we mean when we talk about the orthonormality or orthogonality of functions. So same, these kind of orthogonality and orthonormality we talked about. So when we discussed these Legendre polynomials, so in case of Legendre polynomials, the inner product between two Legendre polynomials PLX and PMX, so this is how these Legendre polynomials are indexed from -1 to 1. So it is given by this 2 by 2l plus 1 times delta of l comma m. So if it means that when l not is equals to m, that means if we are choosing two different Legendre polynomials, in that case the inner product between them will be 0. So that means these Legendre polynomials, they are indeed orthogonal. But the inner product with itself, when l equals to m, in that case the inner product with itself is not 1 because of this factor present. And as a result, we will say that these PLX, these Legendre polynomials, are not normalized. So if you want to normalize it, then what you need to do is, so this is basically kind of mod square, so inner product with itself. So it's kind of in case of vector, it will be the length of the vector squared. So what we need to do to get things normalized is basically we need to divide the Legendre polynomials by square root of this star. That's what we are doing it here. So to normalize the Legendre polynomials, what we are doing is we are dividing the Legendre polynomial by square root of the mod square term. This is what we will call the normalized Legendre polynomials. And as we are getting these Legendre polynomials as a set of as a series of orthogonal functions, in that case, if we take any functions between -1 to 1 defined in the range -1 to 1, then I can expand it as a linear combination of these Legendre functions, Legendre polynomials, and that's what we will be calling the Legendre series. This expansion we will be calling the Legendre series, where this CL, these constant coefficients, these can be written like this. So all these things were discussed while we talked about this orthogonality of Legendre polynomials. And if you want to know more about it, then the link of the video is given in the description section. Please have a look at it. And now let's go back to the orthogonality of Bessel functions. If we recall again the orthogonality of Legendre polynomials, that is integration from -1 to 1 PLX PMX dx equals to 2 by 2l plus 1 delta of lm. So here it is saying that if you take two different Legendre polynomials, two different solutions of this Legendre differential equation, those are basically the two different Legendre polynomials, then those are orthogonal. Similarly, one might think that in case of Bessel functions also, if we take two Bessel functions, let's say jpx and jqx, p naught is equals to q, in that case maybe somehow we can define some kind of integral, and then I can make them 0, and I can call this jpx and jqx, two different Bessel functions. These are orthogonal, but that is not the case. In fact, those are not orthogonal. If we take two different Bessel functions of first kind, for example, those are not orthogonal. So the proof, I will not be doing that. So I'm just stating that this JP's, the Bessel function of first kind was for different values of P are not orthogonal. So in case of Legendre functions, Legendre polynomials, we had that, but in case of Bessel functions, the orthogonality is not defined like that. So how does it how this orthogonality is defined? So let me explain it. So let's make a comparison between sine functions and these Bessel functions. So let's take this sine x or cos x, and in the right hand side let's take this Bessel functions jpx or this Newman functions, second Bessel function of second kind. And in case of this sine or cos functions, so for example in case of sine x, the zeros of sine x is at x equals to n pi. I think we all know that. It's because when you plot, so if I write sine of n pi, it means that sine of n pi equals to 0. So at x equals to n pi, the sine of x will be 0. When this n is 1, 2, dot, 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 1, 2, 3, 4, taking the integer values. Now, we know that for Bessel functions also, these kind of zeros exist. So I will not talk about different Bessel functions, different values of P. So let's fix the value of P. So let's fix the value of P. So all I will be talking about for a particular value of P. So I will not say that for two different values of P, the Bessel function will be orthogonal. That's not the case. Let's fix the value of P, and let's assume that the zeros of jpx are at x equals to alpha 1, alpha 2, alpha 3, comma dot dot dot. Okay, so we have already seen that there are infinite number of zeros present in case of jpx, and we talked about some of them. So it means that jp at x equals to, let's say, alpha n equals to 0 for n equals to 1, 2, dot dot dot. So these are alpha 1, alpha 2, these are some points on x axis where the value of this jpx will be 0. So just like for sine functions we can find the zeros, for Bessel functions also we can find the zeros. Now the differential equation satisfied by y equals to sine of n pi x. So now I am talking about a function, so that is sine of n pi x, where this n pi is basically the zeros of sine x. So for y equals to sine of n pi x, so for sine x, this n pi, x equals to n pi, these are the zeros. Now if I define a new function that is sine of n pi x, so in that case the zeros will be x equals to 1, or x equals to at x equals to 1 it will be 0. So the differential equation satisfied by this sine of n pi x, it's basically y double dash plus n pi whole square y equals to 0, and the orthogonality condition is given by the orthogonality condition is given like integration from 0 to 1 sine of n pi x times sine of m pi x dx equals to 0 if m not is equals to n. So prove it as a homework. It's a very easy proof. So prove this relation as a homework. And similarly, we will define the orthogonality in case of Bessel functions. So similarly, these Bessel functions, Bessel functions, the differential equation satisfied by, let's say y equals to, I am defining a new function which is jp, and instead of x I will be writing alpha n x. So this alpha n is basically the zeros of this jpx. So now it will be 0 at x equals to 1 because the way I am defining it. So y will be 0 at x equals to 1. So the differential equation satisfied by this y satisfied by this jp of alpha n x is basically x square y double dash plus xy dash plus alpha n square x square minus p square times y equals to 0. So instead of x I am writing alpha n x in this differential equation of Bessel for Bessel function. Instead of x I am writing alpha n x. So that's why here I wrote alpha n x, but here I didn't wrote it. It's because in the y double dash x there is 2x present here. So y double dash x is nothing but d2y dx2. So, and from here there will be alpha n square coming out, and it will get cancelled by this alpha n square that will be coming out from this x square. And similarly for this term also, So our new function y, which is defined like this, satisfies this differential equation, and the orthogonality for this jp of alpha n x, it is defined like this: 0 to 1 jp alpha n x times jp alpha mx, so times dx equals to 0 if m not is equals to n. So if I take the same jpx, the p's I am not changing, what I am looking at it at different zeros. So this alpha n and alpha m, these are different zeros of these Bessel functions. So this orthogonality statement, it can be stated in two ways. One way is basically we are saying that, sorry, there is x multiplied here. So x times jp alpha n x times jp alpha mx dx equals to 0. So we are basically saying that root under x times jp alpha nx are orthogonal on x belongs to 0 to 1 in this interval for different alpha n. So if we choose different zeros, in that case this function root under x jp alpha nx, these are orthogonal to each other. So it means basically this root under x jp alpha nx times root under x jp alpha mx dx equals to 0, integration from 0 to 1. And this root x, these are, if I multiply them, then this is just x. This is what I wrote here, you know. So this jp alpha x and jp, so this jp alpha nx, these are not directly orthogonal. Root under x times jp alpha nx, these are actually orthogonal. Or this is one statement. Another statement might be that jp alpha nx are orthogonal on x belongs to 0 to 1 for different alpha n with respect to the weight function wx equals to x. So this is what it means, like x, this is what it's meant by x jp alpha nx jp alpha mx dx equals to 0 for m not is equals to n. So these are directly not orthogonal. This jp alpha nx, these are not directly orthogonal. Subjected to a weight function which is x, these are orthogonal. So it can be stated like this, or it can be stated like this. Now let me prove that this is indeed the case, like subjected to this weight function x, this jp of alpha nx and jp of alpha mx, the inner product between them is 0 for m not is equals to n. Proof of orthogonality. And here this orthogonality doesn't mean that if we take two different jpx for two different values of p, the Bessel functions will be orthogonal. That's not what it means. It means if we take two different zeros of these Bessel functions, that is alpha n and alpha m, so this alpha n and alpha m, and if we do the inner product between this jp of alpha nx with jp of alpha mx subjected to this weight function x, then the inner product will be 0. That's what it means by orthogonality of Bessel functions, and let me prove it. The Bessel differential equation is given by x square y double dash plus x y dash plus x square minus p square times y equals to 0. Let me write it. Let me write these y. So these y are not jpx. These y are basically jp of alpha nx. So let me write them as y tilde. Fine. So these y, these are the direct solution of this Bessel differential equation. But these functions, these y tilde, which are jp of alpha nx, these satisfy a different equation. Now this Bessel differential equation, it can also be written as, so let me write it, these two terms I can write it as if I take x common, then I can write it as x y double dash plus y dash, and this term can be written as x y dash whole dashed. So it means that d dx of x y dash. So it basically means that if I take x intact and derivative this y dashed with respect to x, then it will be x y double dashed. And if I for the next term, if I take this y dashed intact and do the derivative of x with respect to x, then it will be 1. So as a result, I can write this equation as x times x y dashed whole dashed plus x square minus p square times y equals to 0. This is the Bessel differential equation. And now for j of alpha n equals to 0, so for a 0 of Bessel function, which is in this case alpha n, let's say jpx. So I am fixing the value of p for some particular value of p. The differential equation for the newly defined function that we have defined by y tilde, which is jp of alpha n x, and let me call it u, instead of y tilde, let me call it u. So the differential equation for this jp of alpha n x is x times x y dashed of whole dash plus alpha n square x square minus p square times u equals to 0. So that's what I showed here also. Here also I showed the same thing. So in the Bessel differential equation, instead of x I am writing alpha n x. So I'm just writing alpha n x, and that will give me the differential equation for jp of alpha n x. And here it is not changing because in the differentiation, so it is differentiated with respect to x, and then this alpha n, it will get cancelled from numerator and denominator. And let me call this, okay, this is not y, this is now u, sorry, this is u. So this equation is for newly defined function, that is y tilde. So similarly here this equation is for u. So let me call it equation 1. And now for another 0 of Bessel function, let me call it jp of alpha m, that should be equals to 0 because alpha m is a 0 of Bessel function. So here alpha m not is equals to alpha n. In that case, the differential equation for the newly defined function, let me call it v, which is jp of alpha mx is x times x v dash whole dash plus alpha m square x square minus p square times v equals to 0. So let me call it equation 2. So these are the two equations satisfied by this new function, that is jp of alpha mx or alpha nx, whatever. And now what I will do is I will multiply this equation 1 by v. So I will multiply this equation 1 by v and then I will multiply this equation 2 by u, multiply this equation 2 by u, and subtract this from this. And if I do that, then I will get, so it will be then from equation 1 I will get v times x u dash whole dash plus alpha n square x square minus p square uv equals to and then I need to multiply this u with equation 2, that will be u times x v dashed whole dashed plus alpha m square x square minus p square times uv, and I need to subtract this from this. So then I should write a minus sign here, and I should write a minus sign here. And if I subtract the right hand side of the both equations, then it will be 0, because those are already 0. And now you can see that this minus p square, it will get cancelled with this p square, because here this minus it will be plus, and the same factor uv are multiplied with both the terms. So then we are left with vx times x u dashed whole dashed minus ux times x v dashed whole dashed plus, if I take this x square outside, if I take this x square common, then I will get alpha n square minus alpha m square times x square times uv, and equals to 0. Now x is a variable, so in that case it can take any value, it can take value other than zeros also. So in that case I can cancel this x, so I can divide this whole thing by x, and then I will get v times x u dashed whole dashed minus u times x v dashed whole dashed plus alpha n square minus alpha m square x u v equals to 0. And now if I look at this term, this is nothing but ddx of vx u dashed minus ux v dashed. No, you can just show it here, you can just prove it as a homework, that if you do the ddx of this term, then you will get 4 terms basically, if you treat them these 2 terms and these 2 terms together, and 2 of them will get cancelled. So I can write it as ddx of vx u dash vx u dashed minus ux v dashed plus alpha n square minus alpha m square x u v equals to 0. And now what I will do is I will integrate both left hand side and right hand side with respect to dx from 0 to 1. And in the right hand side it will be 0. So now if I do this integration, let me do this integration first. It will be, so ddx of this times dx, so it is basically d of this whole term, and integration of this will be just vx u dashed minus ux v dashed from 0 to 1. So if I put the lower limit 0, then because of this x present, it will be 0. And now if I put this upper limit 1, in that case this v will be, so v, what is v? V as a function of x. V is let's check here, p is jp of alpha mx. So v is jp of alpha mx. Similarly, u as a function of x is jp of alpha nx, right? And now if I put the upper limit 1, in that case it will be v of 1, which is jp of alpha m. Similarly, for this term, in this u, if I put the upper limit, then it will be u of 1, which will be jp of alpha n, and this alpha m and alpha n, these are the zeros of Bessel function. That means jp of alpha m will be 0. Similarly, jp of alpha n will be 0. So when we put the upper limit also, it will be 0. So basically this integration, it is nothing but 0. This integration, the first term is 0, the first integration, and we are left with the second integration. So basically what we are left with is integration from 0 to 1, and this is a constant term, it has no x dependence, so I can put this outside this integration. So I will write this alpha n square minus alpha m square, then integration from 0 to 1 x times, what is u? Ux our jp of alpha nx times v. What is v? V is jp of alpha mx dx equals to 0. And now we have already assumed that we will be considering two different zeros, right? So that means that alpha n not is equals to alpha n. So in that case, this jp of alpha nx and jp of alpha mx, those will be orthogonal, subjected to this weight factor. And in that case, this alpha n square minus alpha m square, it not is equals to 0. So the only condition, the only result we can have from there is this integration should be equals to 0. So basically what we just proved is integration from 0 to 1 x jp of alpha nx times jp of alpha mx dx equals to 0 when alpha n not is equals to alpha m. This is the orthogonality of Bessel functions. This is how it is defined. It is not like the Legendre polynomials. Now let me talk about the normalization of these Bessel functions. So normalization. Here I will assume that alpha, let's take a 0 of Bessel functions, that is alpha. So in that case, jp of alpha equals to 0. So alpha is a 0 of Bessel functions. For example, if let's say this is a Bessel function, so in that case, this is the x, and let's say this is the jpx. So then this is alpha. This is at x equals to alpha. And let's take another variable beta. Beta may be 0 or may not be 0 of this Bessel function. So we have then jp beta, and it may be 0, it may not be 0. Now if I define two functions, for example u, which is jp alpha x, and v, which is jp beta x. In that case, this u and v, these two will satisfy this equation. These two will satisfy this equation. This equation. This equation. Because you can see that till now we have not used the fact that this alpha n and alpha m, these are the zeros of this Bessel function. So here, while putting the limit, we have used it. So now if this beta, even if it is not a zero of this Bessel function, it will satisfy this equation. Okay, where this alpha n, I can call it alpha, and this alpha m, I can call it beta. So then I can safely write that integration from 0 to 1 ddx of vx u dashed minus ux v dashed, vx u dashed minus ux v dashed dx plus this, so plus integration from 0 to 1, and instead of alpha m, instead of alpha n, I will be writing alpha and alpha square minus beta square, and so instead of alpha m I wrote beta, and then x u v dx. So x u v dx equals to 0. So this u and v, this is basically, this u is jp of alpha x and v is jp of beta x, and where this alpha is a zero of Bessel function, but beta may not be a zero of Bessel function. Beta can be any point on the x-axis. Now if you concentrate on this first integral, then it will be v x u dashed minus ux v dashed, and the limit will be going from 0 to 1. The upper limit will be 1, and the lower limit will be 0. Now if I put the limit, if I put the lower limit, then because of this x present here, it will be 0. So now if I put the upper limit, then so u we have j of p alpha x, v we have j of p beta x, and u dashed, sorry, it's not v dashed, it's u dashed. So u dashed we have so ddx of, this is ddx of jp alpha x, which means it is jp dashed alpha x times ddx of alpha x, which is nothing but alpha. Similarly, v dashed will be beta times jp dashed of beta x. And we also know that u at x equals to 1, which is nothing but jp of alpha, equals to 0, because this alpha is a 0 of this Bessel function. So now if I put the upper limit, then from this first term it will be, so v at x equals to 1, so it will be then jp beta times, so then x equals to 1, so times 1 times u dashed, and u dashed is alpha of jp dashed alpha x, so it is alpha times jp dashed alpha, and x is 1 because I'm putting the upper limit, so it is just this, and minus, now if I put the upper limit in this term, then it is u of 1, and what is u of 1 here? U of 1 is jp of alpha, which is 0. It's because this alpha is a 0 of Bessel function, so that means the other term will be 0. So this first integral will only give this term. So in that case, I can write this entire equation. I can write this entire equation as jp beta times alpha times jp dash alpha plus integration from 0 to 1. So I can take this alpha square minus beta square outside of the integral because it doesn't depend on x. So it is alpha square minus beta square, then integration from 0 to 1 x u v dx. So x, and what is u? U is jp of alpha x, jp of alpha x. What is v? V is jp of beta x dx equals to 0. Also, one thing I can do is I can take this minus outside. In that case, I can put here a minus sign and I can interchange this alpha and beta. So it will be beta square minus alpha square. And now if I take this term to the other side of this integration, then it will be 0 to integration from 0 to 1 x. So this integration will be x jp of alpha x times jp of beta x dx. It will be jp beta times alpha times jp dash alpha divided by beta square minus alpha square. So let me draw it again, that what are these alpha and beta. Let's say this is the x-axis and this is our jp x. In that case, let's say this is our jpx plot. So this is our alpha, because alpha is the 0 of this Bessel function. So at x equals to alpha, the Bessel function will be 0. And beta, it can be any other point. So this is the beta. Now what I will do is I will what I'm trying to get, I'm trying to find out this integration 0 to 1 x jp of alpha x times jp of alpha x dx equals to what. So this will tell me whether our these Bessel functions, this jp of alpha x, these are normalized or not. So if this is 1, then up to this with respect to this weight factor, this jp of alpha x, those are normalized, and if not, then it will tell me what should we do to get them normalized. So we want to multiply this jp alpha x with jp with itself, jp alpha x. So for that, what I will do in this equation is I will consider this alpha as a fixed point, and I will move this beta towards alpha. I will move this beta towards alpha. So what I will do is basically limit beta tends to alpha. I will take the limit beta tends to alpha both sides. Integration from 0 to 1 x jp of alpha x times jp of beta x dx equals to limit beta tending to alpha jp beta alpha jp alpha jp dash alpha, sorry, jp dash alpha divided by beta square minus alpha square divided by beta square minus alpha square. Now here if in the left hand side, if I took the limit beta tends to alpha, then this jp of beta x, it simply becomes jp of alpha x. So in the left hand side, it is limit integration from 0 to 1 x jp of alpha x times jp of alpha x dx equals to, now if you look at this right hand side, then in the denominator beta square minus alpha square, and as we take beta towards alpha, then this will be go towards 0. Also in the numerator, because this alpha is a 0 of Bessel function, so in that case, when beta is going towards alpha, then this jp of beta, it will be going towards 0. So it's basically a 0 by 0 form. Then what I will do is I will do the L'Hospital. I will use the L'Hospital rule, so which tells me that it becomes del beta of this numerator divided by del beta of this denominator. And if I do this del beta, I'm treating this alpha as a fixed number, So in that case, it will just be jp dash beta times alpha times jp dash alpha, and for the denominator it will be twice beta. And now if I take the limit, then it will be jp dash alpha times alpha jp dash alpha divided by twice alpha. No? In place of beta, I am writing alpha. And this alpha will cancel, and what we are getting is basically integration from 0 to 1 x jp alpha x times jp alpha x dx equals to jp dash alpha whole square divided by 2. So it is showing that this jp of alpha x with respect to this weight factor x, this is the weight factor, it is not normalized. And in order to normalize this Bessel functions, so this normalized version is basically root under x jp of alpha x and then divided by square root of this. So divided by square root of this, square root of this jp dash alpha square divided by 2, and which is nothing but root 2 divided by jp dash alpha. So this is a normalized version. And now if I write this equation and the orthogonality equation together, this equation together, then what I will get is 0 to 1 x jp of alpha n x times jp of alpha mx dx equals to jp dash of alpha m or alpha n, whatever, whole square divided by 2 times delta of mn. So this is the orthonormality condition for Bessel function. Orthonormality condition. So this is what we mean when we call these Bessel functions are normalized. So it is not like the Legendre polynomials. Now the thing that is left is basically the Bessel series. Because we just proved that this jp of alpha in x, these are orthogonal with respect to this weight function x. So in that case, if we take any function between 0 and 1 or any range, I can write it in terms of these Bessel functions, as a linear combination of these Bessel functions. So those we will be calling the Bessel series. So that thing I put it in the assignment. So I will just attach the assignment in the description section. So please go through the assignment and solve them. Don't get panicked by the lengthy questions. The questions are very easy, and you will get a very good idea about what do we mean by Bessel series and this orthogonality once you solve those three problems in the assignment. So that's all for today. In the next class, I will talk about some different kind of Bessel functions. So bye.